stochastic optimization in wind engineering application. So we divided this package in two parts. So first, I present a synthetic wind generator, and then Anoop will continue with optimization. So this is the general framework for optimization of the shape of the tall building. We need to generate the wind turbulence field. So for this we need to generate synthetic wind inflow. So here in the inlet surface. So how it's implemented? So we generate synthetic one big block of synthetic one 3D block of synthetic wind, and then separate in one direction on different snapshots. In this case, the third direction represents the time, and then we substitute these snapshots as in inlet boundary condition. However, the question how to generate synthetic turbulence model, the turbulence field. So here I going to present you the model for synthetic wind generator. So the basic thing that we the velocity is separated on the mean profile and fluctuation, random fluctuation. This random fluctuation is in fact random field, vector random field. So this fluctuation is basic. So the most simple model is to generate this as a Gaussian random field. That means that it's simple convolution of Gaussian white noise. Here, XI, it's a Gaussian white noise. And we convolve this. Here, F represents Fourier transform. So we apply Fourier transform, then multiply pointwise with some kernel function, Fourier back. So it's simple convolution with some covariance kernel. And here it's the crucial point here. What is the covariance? Because the covariance function here describe physical and statistical properties of the generated field. Let me define the notion of the spectral velocity tensor. Here G, we call it correlation. So this is actually it's the kind of square root of correlation function, and of the spectrum of this square root of correlation function. And phi is denotes here the spectrum of the correlation function itself. So how it looks like, there are a lot of literature on this topic, and for example, for simple isotropic field, the form of this spectral velocity tensor is known. So we can distinguish several components in this spectral velocity tensor. So this one corresponds, this is the spectrum of curl, simply which guarantee that the obtained field will be divergence free. And then we have the scalar factor, which corresponds to the energy spectrum function. The form is this form is common in the literature. Yeah, it may look difficult, but it's commonly accepted form in the literature. And yeah, and then we can benefit from simplicity of the model, that is Gaussian random field, for so-called on-the-fly generation of the inflow. The principle is that we separate, instead of simulating the big block for all required time at once, we separate this time on different time intervals. different blocks. But here we need that when we put the blocks together, they present uniform. They present contiguous random field. So the principle here that when we generate each block, we present a relatively small with respect to block size, overlapping buffer area. And this area, so two adjoint blocks, they share the white noise, which is used to generate the velocity field in each block. That means that we consider first block, we take the white noise, we correlate it, like this, we generate the velocity field in this block. Then we copy the buffer part and paste for the next block, and then we can use the new noise to continue generate the field in the next block, and so on, and we continue and so on. So on the right, you can see several blocks generated separately, and on the sample B, it's the same blocks which are put together. And then we take different snapshots and use them as inlet boundary condition. But then, as I already told, that this model is the most simple that we can consider. And it's isotropic and doesn't take into account the boundaries. So it barely can describe true physics. And our interest is to model the flow in the inertial sublayer, so it definitely affected by the boundary layer. So how we can take boundary condition into account? It appears that the model that I just described, so the convolution with prescribed with the given kernel, is in fact solution of partial fractional differential equation. Fractional partial differential equation. So here the equation that is Laplacian. So it's solution of fractional differential equation on the free space with constant coefficients. So here L is the constant diffusion coefficient for Laplacian. But for this, if we present our model, if we formulate our model in this form, so in this case, we know how to apply the boundary conditions, how to take into account boundary conditions. And for example, not only boundary condition, but we can also consider variable coefficients. That means the diffusion coefficients may depend also on the position, in particular on the height. Yeah. So what are the boundary conditions? So one of the boundary conditions which should be implemented, it's of course non-penetration boundary condition. So this is the restriction on the normal part of the velocity. And as we formulate our equations in terms of vector potential, such that the velocity is actually the curl of the vector potential. So in terms of vector potential, that will be, we just reformulate this in terms of vector potential. But in this case, we still have one, let's say, free boundary condition. So which, if we apply on the non-penetration boundary condition, we still have one component which is still free. Here we introduce Robin type boundary condition for the third component, such that kappa here, it's the free parameter for the model. And this parameter actually can be learned from, so it's allows some freedom for the model of flexibility, and then it can be learned from the experimental data to find to adjust the real boundary condition, the true boundary condition here. So here the example of isotropic. So this is isotropic model where we introduce initial isotropic model, so constant coefficients equal to L infinity, so its characteristic length, and we introduce a boundary condition on the bottom. And then here you see two extreme cases where the Robin constant kappa is equal to 0 and to infinity. So we see that this Robin constant doesn't affect the vertical direction of the velocity. It will be the same for all kappa, but it will affect the other components. In this case, I remind that u and v direction will be the same. And so kappa between 0 and infinity will lead to the values, boundary values in between these two extreme cases. Moreover, we can not only apply boundary condition, but as I said, we can also introduce the coefficients, diffusion coefficients dependent. So we call it shape operator. So we can introduce shape operator which can depend on the height. But we don't know how it looks like the function, the coefficient, how the coefficient depends on the height. So we introduce parameterization of these coefficients. Here we used as just represent the coefficient as some a linear combination of exponential function with unknown learnable exponents. So all these parameters, all parameterization of the coefficients, along with unknown Robin constant, compose a parameter vector of the parameters, vector of learnable parameters theta. So in this way we formulate the minimization problem. So the parameters vector uniquely define the model. On the other hand, we have data obtained experimentally for Reynolds stress. So in this case, we can infer the parameters from the experimental data. So we just simple minimization of the misfit. We obtain the parameter theta, and on the right you can see the plot for Reynolds stresses, where the dots presents the experimental data, and the lines it's the model. So we can fit using this quite flexible parameterization. We can fit the experimental data for the boundary layer. But Reynolds stress, it's just marginal variance of the field. What if we consider more rich statistical descriptors? One of such descriptors, so it should be more rich descriptor, but in the same way, we need some experimental data to fit the model. So one of such descriptors, which data available, is one-point spectra. One-point spectra, it's simply one-point spectra. It's simply the average of the spectral tensor in two direction orthogonal to the wind direction. So here, K1, it's the frequency corresponding to the direction of the wind flow. So the one spectra is the average with respect to all other directions. Oh. Sorry. And the data is also available for such tensors. Oh, sorry, for such spectrum. So this the results which of the most one of the most used widespread model in the literature, and we see that it approximates the data. So the data is dashed lines, and the model it's represents by the solid lines. We see that it approximates the data, but there are still a big misfit between these two. So what we can do better, actually. So first, we proceed with the same way with a rapid distortion theory, introducing the shear, and then it's introduced also AD lifetime variable. And so the principle that eddy breaks after some amount of time, and it also depends, the lifetime depends on the size of the eddy. So big eddy has a longer lifetime, and small eddies, they breaks immediately. So the idea for the model presented on the previous slide was that tau, which is eddy lifetime, is the function of the wave number. But in this case, eddy lifetime will be uniform. But in fact, in the reality, the lifetime of the eddy lifetime depends not only on the size of the eddy, but also general size, isotropic size, but depends on the differently on different size in different directions, because there are direction of the flow and the orthogonal direction. There is a vertical direction, and orientation of the eddy and the size of eddy in different directions also affect differently the lifetime of each eddy. So we propose to consider the lifetime as a function of whole wave vector. But what is exactly the function? What is this function? What is eddy lifetime function as a function of wave vector? We don't know, but we can present this as a specially designed neural network, and then we can learn from the data what is this function. So to learn the coefficient of the network. So this is the result of calibration of the model. So we take the data, available data, and we learn the coefficient of the neural network. So this is the same data that I just presented 2 slides ago, and we see that this model allows to present more accurate. It leads to more accurate one-point spectrum. And this is the learning process. So this is the objective function, so the misfit. Blue, it's the objective function during the learning process dependent on the iteration, and the red dashed line is the standard model objective function value for the standard model. Yeah. So we can pass to the questions.